Hello and welcome to Lecture 11 of CSE350 Digital Electronics and Power Technique course. Today we are going to discuss about a special kind of logic families that is consist of unipolar logic families. Unipolar logic families. And one of the most important member of the unipolar logic family is MOSFET. Here M stands for metal, O stands for oxide, and S stands for semiconductor. So I think you are already familiar with this topic from your CSE 250 course, 251 course, and you are going to learn a lot about this course in VLSI structure because this is the most important section or most important logic families that are used in modern VLSI techniques. So let's begin. First, we want to investigate the basic internal structures. So here is the two schematic diagram. This is an isometric view and this is a simple cross-sectional view. So you can see here that metal oxide semiconductor structure has a gate here. The gate is mainly made out of metal. It was historically made out of metal, but in today's technique, it is actually the polysilicon is used. Polysilicon has been used for fabricating the gate here, and here you can see that TOX layer, that is actually the oxide layer. So TOX, T stands for the thickness and OX stands for the oxide here, and you can see there are two sections right besides the oxide layer, and these two sections are the diffusion layer. They are called the diffusion layers. So there are two types of diffusion layers. One is denoted as drain. This is drain, and this one is source. So basically, there is no difference between the architecture of the drain part and the source part, and they are actually made out of the similar type of thing. So here you can see and that the base of this metal oxide semiconductor structure is the last part of here is the semiconductor. The semiconductor is made out of p-type materials, and the diffusion layers are made out of N plus type. So N plus type means that the doping concentration of these diffusion layers are considered as higher than the usual p-type concentrations. Okay, so this is the channel length. You can see the distance between the two drain to source layer, and the width of the gate layer is denoted as W. Okay, here is the cross section. In this cross section, you can see again, this is the length here, and this is the drain part, source part, and the other side is actually insulated through the field oxide. And usually we use silicon dioxide for gate oxide actually. And this is the polygate. Polygate actually means that the metal part is now replaced by the polysilicon here. And the P substrate is made out of usually silicon, but there are different type of materials could be used as a substrate, just like gallium arsenide or germanium. It depends on the applications of the VLSI design or the MOSFET structure. Okay. So let's begin the basic operation. So in our discussion, we are going to use mainly NMOS. So N stands for N type, NMOS. This is the metal oxide semiconductor, and N stands for N type, and therefore N also denotes that it is the N channel MOSFET, and the substrate would be the P type substrate. P type substrate here. Okay, so there is a certain parameter that is actually come with the n-type MOSFET, that is called VTN. It is called the threshold voltage. Threshold voltage. Okay, so and this is the body, or the substrate is called the body terminal. This is also known as the body terminal. So body terminal and the source terminal is usually connected to the ground, but there is always a difference whenever we are using sorted body and source. Usually when we are using MOSFET as an individual circuit structure, then the body terminal and the source terminal are shorted. They could be connected to ground or any other voltages, but for this discussion, we are just focusing on this body, and source are connected to the ground. And here you can see the gate terminal is having a voltage that is less than the threshold voltage. And now we are increasing the, we are having a drain voltage. So right now, what is going to happen? There will be no channel will form underneath the oxide layer. Channel means that the accumulation of inverse charges underneath the oxide layer, that is called the channel. So there will be no channel underneath the oxide layer, and therefore there will be no current would be flowing through the drain to the source terminal. Okay, whenever the gate voltage is higher than the threshold voltage, then there will be a inversion charge layer, that is inside the p-type semiconductor there will be a n channel. That means the electron would accumulate inside just here. That means there will be a bridge between the drain to the source terminal through this inversion layer. The inversion layer will be accumulated because of the high voltage that we are applying to the gate terminal. Therefore, there will be much more electron concentration underneath the oxide layer, and therefore the drain terminal would be connected to the source terminal. And whenever this happens, if we increase the voltage at the drain terminal, the current would flow from the drain to the source terminal, and therefore we consider the MOSFET has been turned on. And whenever the gate voltage is less than the threshold voltage, then the MOSFET is turned off. So we should remind you again that this discussion is only valid for NMOS, enhancement type MOSFET, because in case of enhancement type MOSFET, that the threshold voltage is positive. Okay, so you will learn more about this in your next course, VLSI design CSE460. Okay, so another thing to note here that there are different operational mode for MOSFETs. So if the gate voltage is higher than the threshold voltage, we consider the NMOS is turned on. And if the drain voltage is very small, actually we can consider it very close to zero, then the current, the MOSFET would behave like a resistor. So this behavior is almost like a resistor, and we all sometimes call it the linear behavior. That means the difference between the drain to source terminal, the voltage difference between the drain to source terminal would proportionally increase the drain current through this channel. However, if the drain terminal is somewhat higher than the previous standard, then the relationship is not going to be linear anymore. You can see that the relationship is now is kind of parabolic. Actually, we are going to see that the formula for this section is actually a parabola. And later, if the drain voltage minus the gate voltage is now equals to the threshold voltage, that we reach at a point where there is a pinch off happening at the channel region, that you can see the channel is actually pinched off. That means the channel region has been truncated at the drain terminal. So whenever this happens, this condition is called the transition point. transition point. Now, if the drain voltage is higher than the difference between drain to gate voltage is higher than the threshold voltage, then the pinch off or the section is actually moving towards the source terminal, and in that case we reach at the saturation. That means that the drain current is now independent of the drain to source voltage, and this is a very surprising thing, because the channel is now truncated, or the channel is now pinched off to a very narrow region, but the drain current is not slowing down, or the current flow is constant throughout the change of drain to source voltage. So this is called actually the saturation region. So this is saturation, and before this part we call this the triode region. Some book refer it as a linear region, however we will call this as a triode region. So the condition for triode region should be VDS minus VGS is less than VTN. Okay, so the transition point is actually the in between the saturation region and the triode region. There is another region that exists, that is the cutoff region. Whenever the gate voltage is less than threshold voltage, here the gate voltage is higher than the threshold voltage. But if the gate voltage is less than the threshold voltage, we call it cutoff region. Okay, so let's move on. So in this course, we are going to talk about or use actually four different type of MOSFET. There are N-channel depletion, N-channel enhancement, P-channel depletion, and P-channel enhancement. So whenever the gate voltage is positive, here you can see from the chart, the N-channel depletion there is on, and the N-channel enhancement is also on. However, the P-channels are off. Okay, and the gate voltage is 0, then the N-channel depletion mode is on. However, the enhancement N-channel is off, but the P-channel depletion is on. So you can see the contrast here that between the depletion and enhancement mode. That is for in case of N-channel, the enhancement mode is off whenever the gate voltage is 0, but the depletion mode is still on. So it actually means that whenever the threshold voltage is less than 0 for NMOS, we refer to the MOSFET as the depletion type. But whenever the threshold voltage is higher than 0 for NMOS, it is called the enhancement mode. Enhancement type MOSFET. But for the PMOS, the conditions are inverse. That is, for PMOS, just use a different color here. Whenever the threshold voltage is less than 0, for PMOS, it is called enhancement type. Whenever the threshold voltage is greater than 0, for PMOS, it is called the depletion type. Okay, so last but not the least, we are going to discuss about the symbol we are going to use for this type of MOSFET. For VTN, or I should say this depletion type, we are going to use a symbol like this. So we are going to fill up this region with some bold color. That means this is the depletion layer, this is the source terminal, the arrow should be connected to the source, This is gate and the other terminal is drain, and this symbol actually means that the usual direction of current flow is from drain to source. Okay, and for enhancement type, this would be like this. There will be no bridge between the drain terminal and the source terminal here. And in case of 4 PMOS circuits, we'll have like this. This is for PMOS enhancement type. Sorry. The usual location of the source terminal is at the top, and the current is flowing from source to the drain for PMOS, and there will be a small circle right beside the gate terminal in order to distinguish it from PMOS terminal. So this is an NMOS terminal, NMOS transistor. So this is PMOS, and this one is like. So there is a bridge between source to drain terminal. So this terminal is source, this is drain, and this is gate. That's how we will distinguish between all these 4 MOSFET types, and you can actually use these conditions to make sense of this chart. Okay, so let's move on to our next video, where we are going to discuss about the current voltage analysis for MOSFET.